Students, are you able to see the PPT?
Yes, sir.
Yes, sir.
Okay. So in last lecture we started the small signal model of JFET, and here in the PPT, unfortunately, those contents are not saved, right? So here now a small signal model of JFET. Right. So quickly I will write here. Here some important terms like ID. This is drain current. VGS, voltage between gate and source, and VDS is voltage between drain and source. Drain and source. And RDS is the drain on resistance. Right. So now we know that ID is function of hello. Good. Okay. No, sir, we are not willing, sir. Okay, we are not willing right now. So if you conduct the offline, that is continue. Okay, sir. Okay. Okay. Right, sir. Thank you, sir. So ID is function of VGS and VDS, right? In yesterday lecture, we discussed that the value of ID changes with respect to both the voltages, right? So we can describe it as ID is equal to function of VGS and VDS, right? And we give this equation number 1, right? So now we can, now in other words, we can say that the value of ID is partially depends upon VGS and partially it depends upon VDS, right? in both voltages, partially depend upon both the voltages. So we can express this equation by using partial differential equation. So I can write here ID can be described by partial differential equation, right? So it is del I d is equal to del id by del VGS, right? And here we make VDS constant, delta VGS plus del ID by del VDS, right? And here VGS we make the constant, so delta VDS. So this is my equation number 2, right? So now for a small signal, del ID you can write it as delta ID, right? Delta IT. So now you can expression 2. So equation 2 can be written as delta ID is equal to delta ID by delta VGS, right? And here VDS is constant, and here it is delta VGS plus delta ID by delta VDS, and VGS is constant here, and delta VDS. This is my equation number 3. Okay. So now you can say that here both there are two terms. This is my first term, and here this is my second term. So in total there are two terms, right? So now in first term, in first term, so in first term, the small change in ID, you can find the small change in ID with the corresponding small change in VGS, right? So first term is a small change in the drain current ID is due to the small change in VGS. Now here, now if you recall the FET circuit which we discussed earlier, this is a symbol of JFET, right? This is my gate, this is my drain, and this is my source. Okay, and here we have connected a battery source, right? So here you have a voltage drop VDS. This battery is VDD. Okay. And here we have connected another battery like this. So suppose this battery is V, and here we have a voltage drop VGS, right? And current ID current is here in the drain terminal. This is ID, right? So now you see in the first term, right? In the first term. So in the first term, ID, right? In the first term, delta ID, a small change in the drain current. This ID belongs to output side, right? It belongs to output. See, if you want to amplify some signal, right? If you want to amplify some signal, so then what we will do? We will connect the signal here. We will connect the signal here, right? And this signal will serve as VGS. So this is our input signal which we want to amplify. Okay, and here this drain current. So if you connect some resistance at the output side, then you will get the output voltage across this drain, right? So see, for example, suppose you have connected some resistance like this here. Okay, and if you want to measure the output, you will get the output this side. This is your output, right? So so ID, drain current, a small change in the drain current, this belongs to the output side. Whereas delta VGS belongs to input side. right? This belongs to input side, right? So now these two variables, that is a small change in ID due to the corresponding small change in the VGS, where small change in the ID belongs to the output section and small change in the VGS belongs to the input section, right? So these two variables have mutual relationship between them, right? So therefore delta ID and delta VGS have mutual relationship. Mutual right? Now you tell me what is the dimension of delta ID by delta VGS? It is if you see, this is your conductance, right? See, what is the resistance? Resistance is V by I, right? And if you reverse this, if you write I by V, then what is this? This is conductance, right? Or admittance, what you call admittance, same thing, it is conductance, right? So delta ID and delta VGS have mutual relationship, and its dimension and its dimension is of conductance, right? Conductance. Therefore delta ID by delta VGS is called as mutual conductance. Mutual conductance. Mutual mutual conductance or transconductance. Transconductance. right? So it is called as mutual conductance or transconductance, and it is represented by Gm. It is represented by Gm, right? Okay. Now we see in second term. In second term. So now you see in the second term, delta ID belongs to the input output side and delta VDS also belongs to the output side. See here, both belongs to the output side, right? So here delta ID belongs to output side and delta VDS belongs to output side, right? So both belongs to output side, right? So now here in first term, ID belongs to the output side, VDS belongs to the input side, so they have mutual relationship. But now in second term, ID and VDS both belongs to the output side, so they have a self relationship between them, right? And the dimension is also same, that is conductance, and it is the dimension of the conductance, right? So here you can say this delta ID and delta VDS have self relationship. With dimension of conductance, right? With the dimension of conductance and delta ID by delta VDS is called as drain conductance, right? Because both are at the drain side. Drain conductance, and it is represented by GD, right? It is represented by GD. Okay, right. So here in the second term, ID and VDS both are at the drain side. So it is drain conductance represented by GD, and in first term delta ID by delta VGS, this is the mutual inductance represented by GM, represented by GM, right? So now expression 3, this is the expression 3. This expression 3 can be represented as, so now equation 3 can be written as delta ID is equal to GM. See here, this term we are writing GM multiplied by delta VGS plus GD delta VDS, and this is my expression number 4, right? This is my expression number 4. So from this expression 4, you can also write this ID ID is equal to GM V GS plus GD V DS. For AC signal, you can write this, right? So this is your equation number 5, right? So this is our equation number 5. So now here, so here what you can do, this one, here we have written RDS, drain to source. Okay. So this expression again you can write in this way, ID is equal to GM V GS plus VDS divided by RDS. See this GD, right? This GD is a conductance which can be represented by IDS, RDS, right? See how we have represented this GD. We have written this GD as ID by VDS, right? And if you reverse this VDS by ID, this is my drain on resistance, right? Here, see, this is the FET. In this FET, current ID is flowing, and VDS is the voltage drop across this. So VDS by ID will be the resistance of this drain to source and material of this device. So this drain on resistance you are representing by VDS by ID, but GD is ID by VDS. So GD you can also write it as 1 by RDS. So same thing I have written here. In place of GD, I have written in terms of resistance. Now conductance I have written in terms of resistance. So it is VDS by RDS, right? Okay, so I call it as expression number 6. So now you see the drain current. Drain current is the sum of two components. One is GM VGS and another is VDS by RDS. So if you draw this in this way, this is my drain, this is my source, okay, and here we are having the current ID, right? So this current is divided in two branch. One is this and another is this, right? This current is divided in two components, this and this. This component, which is a current source, GM VGS, is a current source. Now you represent this by GM VGS, right? And this resistance is RDS. Same way, how we have drawn the model of BJT. BJT model you may find in this way only, right? So in this, okay, and you extend this. This is our source, right? And here it is gate. Here we have gate, okay, and between gate and source you are having a voltage VGS, right? See, there is in this way it is connected. There is a there is no connection here. There is no connection here. Why there is no connection is shown because you see this VGS. Here you are applying reverse bias. Reverse bias. So when it is a reverse bias, then it gate and source, it is almost isolated because there is a reverse biasing, and a reverse biasing there is a heavy depletion layer. See here. So due to this heavy depletion layer, it is considered as an open circuit, this side between gate and source, right? That's why there is no current flow. IG, you will not find any value of the IG. Gate current is 0 in case of JFET because here gate terminal you have connected as a reverse bias. So there is no current flow in this. So here IG is 0. And when IG will be 0, when there is a heavy resistance, then the current will be 0, right? So this heavy resistance is acts as a open circuit. That's why here you can see this, there is a gap between this here, right? So this is a gap. So this is the model of JFET, right? This is a model of JFET, right? Okay. So tomorrow your one class of Suresh sir, D Suresh sir. At what time D Suresh sir class is there? 2:10.
2:10 hours.
2:10. Okay, so he is going somewhere, so I have to take that class. But I have a class at 2:10 in third year. So I will conduct the class at 4:10, right? By 4:10 you will be free now. Students, are you free at 4:10? Because after Suresh sir, there may be another class.
We
And after
don't know,
that,
sir. IDC course will be happening
when it will start?
tomorrow
It will start from tomorrow.
after 4, sir. Today, sir.
Today it will start.
Yes, sir.
From tomorrow.
Okay, then I will inquire at what time it will start. But I can take at 4:10, right? If you are free, then at 4:10 I will take that class, right? Okay.